In late 2018 and early 2019, the world watched in horror as two brand new Boeing 737 MAX aircraft plummeted from the sky. First, Lion Air Flight 610, just minutes after takeoff from Jakarta, then Ethiopian Airlines Flight 302, shortly after departing Addis Ababa. These crashes, separated by barely 5 months, claimed the lives of 346 people and sparked an unprecedented global aviation crisis. The question on everyone's mind was not if these incidents were related, but why, and how such advanced aircraft could fail so catastrophically. The answer lay deep within the plane's flight control systems, a story of design, pressure, and fatal oversight. The Boeing 737 MAX was touted as the future of narrow-body aviation, a fuel-efficient successor to the incredibly successful 737 series, which had been flying for over 5 decades. Facing fierce competition from Airbus and its A320neo, Boeing was under immense pressure to deliver a modern, competitive aircraft quickly. The MAX promised significant upgrades, primarily new, larger engines designed to offer superior fuel economy. This rapid development, however, came with inherent challenges, as engineers sought to integrate advanced technology into an existing airframe, leading to a crucial compromise that would later contribute to the tragic events. The new CFM LEAP 1B engines for the 737 MAX were significantly larger and heavier than previous models. To maintain ground clearance, Boeing's engineers couldn't simply attach them to the existing wing structure. Instead, the engines had to be mounted further forward and higher on the wing. While this solved the clearance issue, it subtly changed the aircraft's aerodynamic profile, particularly at higher angles of attack. This alteration meant that, under certain flight conditions, the aircraft's nose could tend to pitch up, increasing the risk of a stall. Boeing needed a software solution to counteract this unexpected aerodynamic behavior without redesigning the entire airframe. The solution to the MAX changed aerodynamic behavior was the Maneuvering Characteristics Augmentation System, or MCAS. This automated system was designed to push the aircraft's nose down if it detected a high angle of attack, thereby preventing an aerodynamic stall. Crucially, MCAS was intended to operate in the background, only activating under specific, rare circumstances during manual flight and at high angles of attack. Boeing positioned it as a safety feature that ensured the MAX handled similarly to previous 737 models, eliminating the need for extensive retraining for pilots transitioning to the new aircraft. The critical flaw in MCAS lay not in its intent, but in its implementation. The system relied on data from a single angle of attack (AOA) sensor. If this one sensor failed and provided erroneous data, MCAS would repeatedly push the plane's nose down, believing the aircraft was stalling, even if it wasn't. There was no redundancy, a second AOA sensor was present but not used by MCAS to cross-check data. Furthermore, MCAS could activate multiple times, overpowering pilot inputs to climb, creating a dangerous loop that pilots were largely unprepared for due to minimal disclosure in training manuals. A significant aspect contributing to the crisis was the limited information provided to pilots about MCAS. Boeing's documentation largely downplayed the system, and it was not extensively covered in pilot training materials. The company's goal was to certify the MAX as an evolution of the 737, minimizing the need for costly and time-consuming simulator training. Consequently, most pilots were unaware of MCAS, how it operated, or how to counteract its potential malfunction. This lack of critical knowledge left flight crews ill-equipped to respond when the automated system turned against them in a catastrophic failure. On October 29, 2018, Lion Air Flight 610, a Boeing 737 MAX 8, departed Jakarta. Moments after takeoff, the aircraft began to experience erratic pitch control problems. Investigators later determined that a faulty angle of attack sensor was feeding incorrect data to the MCAS system, causing it to repeatedly push the plane's nose down. The pilots, unaware of MCAS or its behavior, fought desperately to keep the aircraft flying, pulling the nose up while the automated system pushed it down. After a terrifying struggle, the plane ultimately plunged into the Java Sea, killing all 189 people on board. Less than 5 months later, on March 10, 2019, Ethiopian Airlines Flight 302, another 737 MAX 8, took off from Addis Ababa. The flight experienced similar erratic behavior almost immediately after liftoff. Once again, a faulty angle of attack sensor led MCOS to repeatedly command a nose-down pitch. Despite the pilot's valiant efforts to counteract the system, the aircraft rapidly lost control and crashed, killing all 157 passengers and crew. The chilling similarities between the two accidents were undeniable, pointing squarely to a systemic issue with the Boeing 737 MAX and its flight control software. Following the Ethiopian Airlines tragedy, governments and airlines worldwide acted swiftly. China was the first to ground its entire 737 MAX fleet, quickly followed by the European Union, Australia, and eventually, after initial reluctance, the United States Federal Aviation Administration, FAA. This unprecedented global grounding of a new aircraft type sent shockwaves through the aviation industry. Boeing's reputation, once synonymous with reliability and engineering excellence, was severely damaged. Intensive investigations were launched into the aircraft's design, certification process, and the regulatory oversight that had allowed such a critical flaw to persist. In response to the investigations, Boeing undertook a comprehensive software overhaul for MCOS. Key changes included making the system receive input from both angle of attack sensors, activating only once per detected high angle of attack event, and ensuring it could never overpower a pilot's manual control inputs. Additionally, new pilot training modules were developed, mandating simulator training and explicit instruction on MCOS. The recertification process was exhaustive, spanning nearly 2 years, as regulators worldwide meticulously reviewed every change before allowing the 737 MAX to return to service, starting in late 2020. The Boeing 737 MAX tragedies served as a stark, painful lesson for the entire aerospace industry. They highlighted the critical importance of robust design, transparent communication, and comprehensive pilot training. The crisis forced a re-evaluation of the FAA's certification processes and raised questions about the balance between innovation, speed to market, and fundamental safety. It underscored that software, while seemingly intangible, can be as critical to flight safety as any mechanical component, demanding the same rigorous scrutiny and redundancy. Ultimately, the disasters changed how aircraft are designed, regulated, and flown. Today, the Boeing 737 MAX is flying again, but its return has been a cautious one, shadowed by the memory of those lost flights. Boeing continues to work to rebuild trust, not just with airlines and pilots, but with the flying public. The legacy of the crashes remains a powerful reminder of the profound responsibility that comes with designing and building aircraft. The real reason Boeing's new plane crashed twice wasn't a single flaw, but a confluence of factors: a design compromise, an automated systems vulnerability, and a failure in communication and training. It's a story that continues to shape the future of aviation, pushing for greater safety, transparency, and accountability.